Hello everyone, welcome back. Let us continue our discussion on reinforced concrete design. We are in the 12th week and this is our 5th lecture. So in this lecture, we are going to design the beam, and for that we have to apply dead load, live load, earthquake load. And for the earthquake load, we have a very specific design code. As you can see, this is IS 1893, and this code we are going to use. We'll use the provisions in this code in STAAD.Pro. But before we go to the STAAD.Pro modeling and design, let us first see what are the guidelines, major guidelines in this code, and then we'll consider the structure that we modeled earlier and then complete the design today. Now, for this seismic analysis, we will go for a equivalent static analysis. Recall, for the building we modeled earlier, we did static analysis using dead load, live load, and then we also did a modal analysis, right? Now for the design, we will go for equivalent static analysis. What does it mean? It means that the earthquake we are going to apply, which is a dynamic load, but we will convert it into an equivalent lateral static force. And that force we will apply, we will see how to quantify that equivalent lateral force as per this IS code. And then once we apply that load, we will go for a simplified static analysis. Now, this method of equivalent static analysis is applicable for regular buildings. We have an academic complex, and here we can easily adapt this method. And of course, for a low to medium height building, again in our case, we have a two-storied building, and the total height is 8 meters with parapet wall and the other structure at the rooftop. It will not go beyond roughly say 10 to 11 meters. Excuse me. Now, as per this codal provisions, we will see there are different seismic zones and there are different structural configurations also. Now, what are the different seismic zones? There are altogether 5 different. Out of that, one is not effective anymore. So we have 4 seismic zones marked on this map. Now, we'll design this building for Guwahati city, which is actually here in this red zone in the northeast region of India. And if you look at the zone marking, it comes under zone 5. So, we'll see what are the factors for zone 5, and accordingly we will consider them in our design. Now, in this equivalent static analysis, what we do, we quantify the base shear. So if you recall, we have a building that we modeled the governing equation of motion, and say we have, this is the building, and we apply earthquake at the base. Now, obviously, the shear force will act here at this level, which is the base shear, and the expression for base shear VB is equal to capital W times AH. Now, capital W is the seismic weight. So, when we'll consider the model in STAAD.Pro, we have to define the seismic weight, and then that we multiply with the seismic coefficient, which is AH. Now, the expression for AH, as you can see here, it is Z by 2 times I by capital R and SA by G. Now, in the next class, when we'll take up response spectrum analysis, I will actually define this SA by G, but for the time being, let us consider this as a factor. So the first one, Z by 2, this Z comes from different zone, as you can see here. Recall earlier we saw the 5 different zones we have, and then for this zone 5 we have this Z factor as 0.36. Now we have Z by 2 here because we have 2 different levels of earthquake, MCE level and DBE level. Normally we design the structure for design basis earthquake. We will not go into the details of this definition of these levels. So for that you can refer to any earthquake engineering book. But for the time being, we will apply Z by 2. Our Z value is 0.36, which is corresponding to DBE level. Now, importance factor as per this code has 3 options: 1.5 for critical and lifeline structure. For example, if you have a hospital building to design, then for that, this importance factor is 1.5. Now, it is 1.2 for community structures and 1 for the rest. So, we will consider 1 for our analysis. Now, this zone factors, as I said, it comes from table 3, as you can see here. Apart from that, there is a factor R. I will come to that in a minute. Now, this AC by G factor, it is given here for different soil conditions. So, 3 different soil conditions are there: soft soil, medium soil and hard soil. For that, depending upon the natural frequency or fundamental frequency of the structure, we need to estimate this SA by G value. Recall, we discussed about the natural frequency for this Amdahl's system. So this is a 2 degrees of freedom system. So we have omega 1 and omega 2, 2 natural frequencies. Now for our building model instead, we have multiple degrees of freedom. So out of that, the lowest value of the natural frequency is the fundamental natural frequency, and corresponding to that we can find out the time period, and that time period is actually used here. Now depending upon this time period, the value of SA by G is fixed based on the soil quality. So our task whenever we start the design is to first find out the natural frequency and select the soil type at the site, and then that will fix the value of SA by G. The moment we fix that value, we can come here. Of course, we need to define capital R, that we'll do in a minute. So we can quantify this AH, and that if we multiply with the seismic weight, we get the base shear. And we'll see in a minute that how we can distribute this base shear along the height of the building. So the first thing first, we have to identify the first natural frequency of the structure. Now for that, we can adopt 2 different approach. Of course, the one we have discussed in the previous class, that we do a model analysis of the structure, and then from that analysis we can identify the first natural frequency and corresponding time period we can use here. If you recall, our first natural frequency was most likely 3.346 or something like that. I hope that is 3.346 hertz from STAD output. So corresponding to that frequency, we can identify the time period. However, as we progress, we will see code also simplifies that. We can use the simplified expression, and based on that, we can identify what is the time period corresponding to first natural frequency, right? Okay, so now coming to the last factor, which is capital R, it is called response reduction factor. Now, response reduction factor, it actually comes due to the influence of nonlinear behavior of the building, then ductility and redundancy. All these are detailed out in the this IS 1893. Now, this response reduction factor again has different options depending upon the building type. So we have moment frame system. If you recall, we modeled this beam column and that forms a moment frame. So again, for moment frame system, we have different categories. So RC buildings with ordinary moment resisting frame, the response reduction factor is 3. RC buildings with spatial moment resisting frames, it is 5. Similarly, we have other options. There are braced frame buildings also. We have no bracing in our building, so that is not our case. But for braced frame building also we have different options for response reduction. Now for our case we have moment frame system, so we will go for this value of response reduction. So the moment we fix capital R, now we have all the parameters in this equation and we can find out seismic coefficient capital AH, and then we can find out the base shear. So that is straightforward. Now once we identify the base shear, its distribution in the vertical direction is also important. As you can see, it is this schematic diagram is having a building with total height capital H and number of stories are here. So QI is basically the distribution of the base shear as we go along the height of the building. So it is QI is the design lateral force at ith floor. So if we are here, say at this floor, the lateral force, say Fi, that is, or Qi, that is obtained from this expression, right? We have already identified seismic weight. We'll see how to apply that weight in StatPro. And then we know the story height. We can have a non-uniform story height also that we can get from the architectural design, and then we multiply this factor with VB and then we will get QI. Now when we do that in StatPro, it will be done automatically, but if you do a hand calculation, that is the procedure. First you identify the base shear and then its vertical distribution along the height. Okay, now the most important part is the fundamental frequency, because the fundamental frequency of the building can come from the IN analysis, if you recall, and in the previous class we have shown how to do the modal analysis. Now IS 1893 provides some simple expression based on the height of the building, what should be the expected value of the time period. Now again, for different category of building, the empirical expression is different. However, we need to find out the total height of the building from the architectural design, and then based on that we can estimate TA. Now again, there are different types of building for which this TA may vary. As you can see, building with RC structural walls, this is the expression, and we can identify all these parameters, where AW, as you can see here, is the total effective area of walls in the first floor of the building, and you can use this expression to find out AW, and then we can find out this TA. Now for all other buildings, this is the expression, so we'll use this expression to find out the first natural frequency and corresponding time period for our building. So it is 0.09 times capital H divided by square root of D. So H is the height of the building. Again, for that we have a dedicated clause 7.6.2a. You can go through that clause. So and let us use in our case height of the building as 8 meter. Then D is the base dimension of the building at the plinth level along the considered direction of the earthquake shaking. So if you have, say this is the building, and if we consider shaking in this direction, so this dimension we have to consider. If we consider shaking in this direction, then we have to consider this dimension. So for our building, this is the lateral dimension that we should consider depending upon the orientation of the shaking. Recall, at the beginning of STAT modeling, we identified the grid plan, and from that grid plan we get these dimensions, right? So now based on this dimension, Tx is 0.115 seconds and this will be T, actually TZ, because Y in our case is the vertical direction. So TZ is 0.136 second. Now recall omega is equal to 2 pi by T. So for this value of time period, we have 8.69 hertz. See, it is not the value that we obtained from our modal analysis, but because it is specified in the code, we will use this value. So, say this is omega x and omega z is equal to, so this is actually fx. So fy or fz is equal to 1 divided by 0.136, so which is 7.35. Okay, so now let us move over to STAAD modeling and see how we can do the complete design. However, in our analysis, we will actually use this value of t. You can also change that to your actual value of time period that you obtain from the modal analysis. Okay. So here we have the model. Now, in this model, again, what we have to do, we have to first define different load cases. That we'll do in a minute. As you can see, here we have seismic load definition. So let us add that. And here you can see different codal provisions are there. So we'll select out of that IS code. And then using this code, we have to generate for that seismic load. We need to define the zone. So for our case, it is zone 5. Here you can see we have different options of frames. So we have a general building. Importance factor is 1. Soil type is medium. RC frame building. So we have period in X, period in Z, and then if we generate, it will be reflected here. So now we can actually change the values of Tx and Tz. Tx is 0.115. So let us change it here. Similarly, for Tz, we change it to 0.136. And you can also change the response reduction factor accordingly. So now here you see the appropriate zone is applied. So next we have to add the self weight. Recall, seismic weight we have to define. So now member weight, which is uniform. Now this member weight we have to define. It is as we defined previously, So you can see if we apply that, it is applied to this identified element, and then we can go to the text file and very easily apply for the complete structure. So let us copy this part and here this negative sign is not required, so you uniformly apply the load. Otherwise, we have to select one by one all the members and then we have to apply. This is a very easy way to define the seismic loads. Okay. So now let us save it, and if you go to the load definition, we can see here the member weights are applied. So these are the identified members where these loads are applied, right? So now let us apply the floor loads, and again earlier we applied floor loads, so it should be 6.5, and using the height we can identify the appropriate floors and we can apply the load. So this is for the first story, and then we repeat the same for the second story. So now these are the live loads that we earlier applied. And when we do the seismic analysis, a portion of the live load also we have to apply. That we'll do in a minute, following the same strategy. So floor loads, half of the live load we apply along with floor mass when we do the seismic analysis. Okay. Now let us define the load case. So it is a seismic. Now we have to define two load cases along X and along Z. We can also define seismic load along the vertical direction, but because we wish to keep this simple, let us apply earthquake along two lateral direction only. Now these are under the modal case right now, so we will adjust that. For that again, we can very easily do it from the text file. And once we apply that load, then we have to go for further analysis for the design against seismic load. And in fact, for that, there are different load combinations that will be automatically generated along with appropriate load factors that we will see in a minute. However, so the first thing first, we need to readjust these two load cases, and let us do that first. So as you can see, we can do it from this. Here we have seismic load and the direction is X with factor 1. Similarly, for the Z direction, we select the seismic load and then it should be in the Z direction with factor 1. So it means that we apply the full magnitude of the design load first along X and then along Z. Now here you see we have these two load cases under modal analysis. So let us first readjust. So after the definition of floor weight, let us put this two seismic load cases. Now you can see these are the first two load cases, and then we have dead load, live load and modal analysis. Just note the load case numbers 1 and 2 are the earthquake along X and Z, then dead load 3 and live load 4. Now we have to apply the load combination as per Indian Standard Code. So the load combinations are generated, as you can see, with appropriate factors, right? So once we add that, we have these complete load combinations corresponding to different load case number. In fact, these load case numbers we will identify once we complete the design. We'll see which one is the critical load case, and you'll see for different members, these critical load case numbers are different. So as you can see, load case 3 and 4 corresponding to live load, dead load and live load. So it has, under the load case number 7, it has a factor of 1.2 and 1.2. Likewise, if we have load case 1 along with 3 and 4, in load case number 8, we have different load factors. Now in this 10, you see the load factor corresponding to load 1, that is earthquake load along X, is minus 1.2. That means it is applied in the other directions. And it is extremely important because this structure is having some asymmetry in plan. So we have to apply in both the directions and make all possible combinations as per IS codes, right? So likewise, all these factors differ in different load combinations, and just by checking the load case number, you can identify which combinations we are dealing with under which number, okay? Those numbers will appear once we complete the design, and we'll see different members will have different critical load case number. So now, let us First run the analysis. As you can see, there are 23 warnings. We'll see that if some section fails or any other issues are there, then we will identify them. So let us go to post-processing, and here you can see for different load cases we can now plot the bending moment, shear force diagrams, and you can select the different load combinations. Here you see this is a bending moment about Z. Likewise, you can select force or this is the shear along Y. And as you can see, for each and every member, you get the shear force diagram. So likewise, we can select different load case and different combinations also, which will give us the structural response corresponding to that load case. And on the right hand side, you see for all different load case and combinations, we have the force and moment values. Here, this is the torsion for every member. So we can also plot its variation over the length. So we can select a member and we'll get the number. So you can select and just plot that member, and we can see the different values. Here we can also plot the graph. On the right hand side, you have the shear force bending moment diagram, and we can select different elements, and for that we can plot it. So once that is done, now we have to design. Here you can see all different load combinations are there. So the moment you select any element, we can identify the number and cross verify the response corresponding to each and every load case. Okay, so now we have to go for the design. So let us select concrete, and for concrete design we have to identify the code. It is IS 456, and then select the parameters. Now you can see there are different parameters as per this code. So first the compressive strength, then Fy of steel, then yield strength for shear reinforcement, maximum size of main reinforcement, maximum size of secondary reinforcement, likewise minimum size of the main reinforcement and minimum size of the secondary reinforcement. Right. So these are the different parameters, and then we have to define these parameters. So FC, recall, we have M25 concrete. So we define that value here. Likewise, Fe415 steel. Then for the secondary reinforcement also we have Fe415. Maximum size of main reinforcement, let us select 25 for a two-storied building. That should be enough. Likewise, the diameter of other reinforcement we can also select. So now we have to add the design element. So we select beam column for the design, and then here you can see all these parameters are defined. We have to also assign these to the structural members. Likewise, we will select and assign as we did in case of loads. So here you can see we assign all these parameters for the complete structure. In fact, we can assign different parameters. For example, a part of the structure we can select one type of concrete, and then another part we can actually define other type of concrete. Likewise, we can change these parameters. So now they are defined, but first we assign it to the view, but as you can see, that is not the correct way, because we have to identify the beams and then we have to assign. Now it is assigned for each and every element. For that, what we can do, we can select the beams and then we can assign it to view or selected beams. Somehow it's not assigned yet, so let us check it once more. So let us select the beams. So all structural members parallel to X and Z are selected. So assigned to selected beams. Now it is proper. So all columns are now selected. Okay. So now we can run the analysis. Here you can see 24 warnings are there. So let us go to the output file. As you know, design is an iterative process. So first we start the design. Some of the member may fail. As you can see here, some of the members have failed. We'll see which member has failed and what is the reason in a minute. And we have to resolve those issues, right? So here you can identify the beam design. So under this concrete design, if you select beam, so you have for each and every beam, complete design summary is given here. We'll see that in a minute, but here you can identify the beam numbers and that will be highlighted. And for those beam numbers, you can see the design details. Likewise, for columns, you can see the column number at the top, it is 69, and then all the details, steel area, concrete area, then sectional capacity, and also the diameter of the steel, all these checks that we did manually earlier are summarized here. Likewise, you can identify different beams. So for example, this is 69, that's the corner column. Likewise 70, that is the next column. Here you can identify, select one column and get the number, and then see the design details given in the output file. Now, see, this member has failed. See here the beam number is 154. So let us see the beam number 154. And for this beam you can see all these details for this complete element is provided. So now let us identify beam number 154. Here it is. So you can see this small beam, it has failed. So we have to change the sectional parameters. That we'll do in a minute. Likewise, so the next one, this is 156. So we can identify 156. So the beam is there. Others are, as you can see, 163 and 165. So let us identify those two members. So here are the members that have failed. Now for them, we have to modify the sections that we'll do in a minute. So you can see the location of the member that has failed. For that, let us go to the cross section. Let us increase the section size. We can actually change the section size for that particular member, but let us make it simple for the time being. Let us change the section size for all the members, although that is not an economical design, but for the time being, let us try that. Still 24 warnings are there, so let us see the output. So the same member fails. And you can see the reason here. Nominal shear force exceeds tau C max limit. Here for this element, no bar is available for reinforcement. So you can see the member location. So now what we can do, we have already increased the section, so we can play with the other parameters, right? So let us try with a different concrete again. Let us increase it to 30. We can reduce the section size because section size was not important. Now here you can see we have 20 warnings. That means some of them are resolved. Still it fails due to tau C max. So no bar is available for reinforcement. So probably we need to increase the bar size. That we'll see in a minute. The length you can see it is 8 meter. Recall we have a lab for that. The spacing is very high. So another element number 290 fails. 291 also. So let us check 290 and 291. Again, we have to change the cross section. We have already increased the FC value, FCK. So let us edit this. Let us increase the size. Now you can see 15 warnings. So some of them are resolved. Let us see how many of them have passed. So only one section has failed, and this is 291. There are warning for other members. We'll see that whether they are important or not. But for the time being, let us first resolve this one. So member 291, that is the only member now fails. All other have passed. Let us select that element. Let us see the location. So here it is, that small member where a secondary beam actually comes. So you can see the cross section. Right now 650 by 450. We can adjust this cross section. (291) is the member that has failed. So let us define another section. Let us not change all other sections because they have already passed. Let us try with 650 by 550. And we can change only that element, but it is not advisable to change only one location, because then the construction, because you see there is a secondary beam there, so we have to identify the complete beam. Otherwise, if we change a part, then at the time of construction there may be issues. So now let us see the output file. Now it has passed. Still there are some warnings. We'll see the warnings. So you can see deep beam is not designed. Length to beam ratio for number 226 is less than 2.5, and that's because we have a lot of secondary beams. Here for this one it is not so important. So, and then these are the warnings. I'll show you what are the meanings of that. It's because we have multiple commands. You see perform analysis so many times that we can actually remove, and because of that we have these warnings, consecutive analysis commands, and the remainings are for the beams identified as deep beam. So you can see if it is a very small beam, it's actually not small because one secondary beam is landing over the main beam, and that's the reason the length of that individual member highlighted, it is small, and that's the reason actually the ratios are not satisfying. Okay. Likewise, here also you see these are because of these secondary beams landing over the main beam. So all of them are having some warning. Now we can leave these warnings because they are not so important for the time being. So what we'll do, we'll see the load cases once more, and we'll see what are the critical load case corresponding to the design, and what are the values of structural response corresponding to those load case. So here you can see, once you select a member, and there you can plot the response, and the plot is shown here. So the different load cases are identified here. So you can select the load case and you can plot, different structural responses. Now for each and every member, complete details are given here. Here are the different major load cases that we have combined with appropriate load factors. Then the response, if you slide this, you can actually change the value of, see the change in value of fx and f and m over the length of the member. You can also change it from bending to shear, and accordingly the diagrams change. Here are the different load combinations. For every load combination, you can also change and see the different structural response. Now, if you see the beam, here you have the complete design details. As you can see, here you can see the shear design results along with the reinforcement details, and all other section wise reinforcements are defined. Now here you can see the values of different parameters along with, see the load case number here. The critical load case number is 16 for this particular member. So out of all the load combinations, this load case 16 is the critical one. So here is the 16 load case, and you can see it is a combination of load 3 and load 2. And you can also notice the load factors. Now, if you select that load case, say 16, so you can see the different values of forces and moments along the distance, and the plot is also shown here. So you can see the deflection also, and then the deflection in millimeter along the length. So you can see the location of maximum deflection, and that too for different combinations also. Here is the complete details along with the detailing over the length of the member. So you can see the main reinforcement, top and bottom layer of reinforcements along with the shear reinforcements. And all these details we um, covered in our beam design, if you recall. Likewise, for this column, you can identify and you can see the complete design details. You can identify the critical load case number from the output file and then select that to plot the response. Here is the deflection. So for this column number 69, you see all the details are highlighted here. And you can see the load case number is 18 and the sectional capacities are also marked. Here you can select the critical load case. The number is 18 for this member, and then go through the complete details. Likewise, for every member, you can cross-verify whether the designs are okay or not. If there is some issue, like we had earlier, accordingly you can adjust different parameters and then you can redesign the cross-section to make it safe, right? So with that, let us close here. Just go through this details and let us know if you have any doubt or not. Thank you very much.